do just that. And then from this, we can use our calculator and we will find that the arctan of 1.7 is 59.534 degrees. Do you get that on your calculator?
I think I will. Yeah, 59.53 degrees.
Awesome. So that way, we're going to solve for the problem in B and for the problem in C. So let's do B. I'm going to ask you what we do next, ne? So that we can both understand that you are learning. So we've got sine theta equals 0.8. What do we do next? What can we do next?
We sine arc, that sine -1 times by 0.8.
Yes, we've taken the arc of the trig ratio for sine. So we're going to say 0.8 arc sine, and that gives us 53.130 degrees. Yes? Ne?
Yes.
All right. And the last one is cos alpha. And this time they use alpha instead of theta, but the premise is the same. We work on them the same. Ne? So cos alpha is 0.32. So what do we do next? We make alpha the subject of the formula by taking the arc of the trigonometric ratio for the number 0.32. And that gives us 0.32 arc cos 71.337 degrees. So far, easy peasy, ne?
Yes.
All right, so we're gonna do the next batch of problems for determining the angle. So this is just find angle. So n is the tan of theta divided by 3. Theta divided by 3 is an angle, and this equals sine of 48 degrees. Ne? So what do we do next? We can first calculate the sine of 48 and get a decimal value. So let's do that. Can you work out the sine of 48?
0.73, but probably doing the wrong.
Yeah, no. It's 0.743.
0.743.
Yes, so you're still correct. Right. So now that we've got the trig ratio, we must now work out theta over 3 by finding the arctan of 0.743. Yeah? But here, just pay attention.
Yeah.
We will need to apply a multiplicative inverse because theta over 3 is a third of theta. So the tan of a third of theta equals the sine of 48 degrees. That's what this initial expression tells us. So now when we solve it, we can say multiplicative inverse 3 arctan 0.743 . Right? So we can now take the arctan of this and multiply it by 3 to get 109.853 degrees. You see that? This one, is it?
Yeah.
Is it? Can you still follow this kind of problem though?
Yeah. Let's see. Let's do another one.
Let's do another one. Okay, that's cool. So the next one is O, which is a half the cos of 2 times beta 2 times beta is an angle, but the actual size that we're interested in is beta, right? And this equals 0.3. So because this is an equation, we can start first with multiplicative inverses so that the cos of 2 times beta, bless you, equals 0.6. Bless you. Are we still following here? So I multiplied by 2 on both sides to remove the fraction on the left-hand side, but I also have to multiply by 2 on the right-hand side, so I double the 0.3. But what that leaves me with...
You haven't done any calculation. Oh, okay, I see that you multiplied.
Yes, I did a multiplicative inverse here. Correct. So from the multiplicative inverse step, we get cos of 2 times beta equals 0.6. And now we must find...
No, sorry, this will take you back.
Yeah.
You've left out the half.
I left out the half.
You haven't calculated the half. Why did you only focus on the cos 2 beta?
Oh no, but I did work out the half because I multiplied with a multiplicative inverse. To illustrate, it's going to be a half times 2, and then I'll just... Right? So when I multiply by 2 across the equation, then the half gets reduced to 1. So I get 1 times cos 2 beta, and I get 0.3 times 2 on the right-hand side of the equation. Therefore, I am only left with cos of 2 times beta equals 0.6. That's why the step looked like it skipped something, because this here and this here happened. I like that you asked that question because it shows that you're paying attention to the detail. And the devil is really in the detail, because as you get to like grade 2, and I'll keep emphasizing this, when you get further and further in your math, by the time you get to grade 12, some steps are expected to be intrinsic. So you'll still get full marks for multiplicative inverse, even though you skip the step, but the next step shows that you did apply the multiplicative inverse.
Okay.
Yeah, and also doing the math mentally saves you time. Remember, it's 150 marks for the exam, 150 marks in 3 hours. So if you take, how many minutes is 3 hours? It's 180. So if you take the number of marks, 150, and you divide it by the number of minutes, that means each mark is about 80% of a minute. So it's just under a minute for every mark that you allocated, that you must allocate time for when you're answering. So when you skip steps by calculating via inspection and doing the mental math and then showing in the next step that you did do it, you still get full credit. But it's kudos to you for identifying that, because it shows that you're smart enough to realize that I gotta save time because I gotta move. Yeah, one. So now we have 2 times beta equals the arc cos of 0.6, and beta then becomes the arc cos of 0.6 divided by 2, because whatever value I'm going to get here, I'll still need to divide by 2 so that I get the value of beta. And when we do the math, 0.6 times Ndweki and then divide by 2, we get 26.565 degrees. In this problem, is there anything that you might feel you need clarity on?
No, I'm fine.
You're fine. All right, so let's do the last one, P. P for Mr. P. Joe would be so annoyed if I say that. 2 sine 3 theta plus 1 equals 2.6. So this one, it's it's literally an equation, but it's also the stuff of nightmares in trig, especially in grade 10. But in matric, you're expected to be familiar with this, né? So I'm introducing this harder one so that you can, be closer to where we need to be for our matric math. So the 2 sine of 3 theta plus 1 equals 2.6. Solving for an equation, additive inverses. Can you see that? Can you see where we'll need to do additive inverses? On slide 3 of Jamboard.
I'm on slide 3, yeah.
You're on slide 3. Okay, cool. So where was I? Yeah. So yeah, additive inverses. Remember, our main focus is here, is on the theta. So we need to eliminate, or rather manipulate our equation so that on the left-hand side, we're only left with theta. And the manipulation is our simple tricks. It's our additive inverses. It's what we do on the left, we do on the right. It's our multiplicative inverses. So we'll start first with additive inverses. And the importance of that is because if we start out with just dividing by 2, so let's say we take out the multiplicative inverses. So we divide by 2, we will have sine of 3 theta plus a half equals 1.3. And we'll still need to do additive inverses such that sine 3 theta is 1,3 minus 0.5 would be 0,8. And then we can do the thing. Alternatively, from this step, we can say minus a half such that 2 sine 3 theta equals 1.3. Yeah, that is correct, right? 2.6.
Yeah.
0.5. Sorry, it's supposed to be 2.1, not
1.1.
Sorry, I'm minusing 0.5 from 2.6. So the answer is 2.1. Yes, that's what's happening. And then the second step, I'll have to divide by 2 such that sine 3 theta equals, let's divide by 2, 1,05. So there's something incorrect that I did here, and I need to check myself that I did on this end here. I'm supposed to be getting the same answer here at this step. So because there's a discrepancy, there's something wrong that I did in either step. So we're going to investigate. So if we start here by dividing by 2, what's 2.6 divided by 2? It's 1.3. And if I subtract a half, 0.8. Huh. Oh, okay. Okay, this is interesting. I want to see what we'll get for theta going forward. Anyway, 3 theta equals the arc sine of 0.8. But this thing is not sitting well with me because how am I getting 3? Yeah, because this one is not going to be correct, because already we've got sine of 3 theta is greater than 1. So maybe not. This method here on the right might not be the best. And that's because already, no, but let me start from scratch. So it's 2 sine 3 theta plus 1 equals 2,6. Sine 3 theta plus 1 over 2 equals 1. Oh, okay. I made a mistake. I'll correct it. I just want to finish this part here. And then, yes, 0.8. Yes, so we are indeed supposed to get 0.8. So I made a mistake here and I'm going to correct it. I'm going to correct it. So what I neglected to look at here is that I ought to have subtracted 1 instead of a half. Here,
Okay.
so it's supposed to be minus 1 so that 2 sine 3 theta equals 1.6. Yes. So that when you divide by 2, then the 1.6 becomes 0.8. And then we are left with working out the arcsine of 0.8, and that equals 3 theta. Which means that theta is arcsine of 0.8 divided by 3, and this is what? 17.710 degrees. Yes. So far, is it clear? There's a hesitation in your voice. There's a hesitation in your voice. Where's the hesitation? Where can we pin it?
I'm following.
Are you sure?
Yeah.
Sure.
Too many shows.
Too many shows. Okay, but the long story short, this is still an equation, and apart from where we have to work on the trig ratio, we still apply the same process to solve equations right up until we get to the answer. All right, so I want us to do the next type of problem where we're given x equals 16 degrees and y is 36 degrees. Né? X is 16, y is 36. So the first one, A, they want us to solve for, or rather to find the value of this trig ratio, sine of x minus y, right? And we also have to do, let's do tan of x minus tan of y. Let's do cos, oh no, let's rather do g. Let's do number g. 2 cos x plus cos of 3y. That's g. And I think we'll do f because I want to reinforce the reciprocal trig ratios. Remember reciprocals, sec and cosec and cotan. Yes, I want us to just emphasize that. Yeah, so it's A, B, and G and F. Yeah. So A, B, and then G and F. All right, so let's start with A. It's sine of x minus y equals, so now we must substitute. What's the value for x?
16 degrees.
16 degrees. And the value for y?
36.
36. All right, so what we have is 16 minus 36 is how much?
20.
20. So now we must find this. Oh no, it's negative 20. Negative 20, not 20. Check that again. 16 minus 36 is negative 20.
It's small minus big.
Yeah, small minus big gives us negative. So now we must find the sine of negative 20 degrees. And that gives us negative 0.342.
Do Do you want to tell why we didn't do an arc of the trig ratio for the sine here?
Oh, because we already have the angle measures. These are the angles.
You explained it to me before.
Eh? Ask again. I didn't hear that.
You explained this to me before.
I did. Did I?
I know.
I don't think we did, but there was no need. And here's why there's no need. So with this type of problem, I want you to notice two things, right? The first one, we're given the value for x. And the second one, we're also given the value for y.
Yeah.
So in order to evaluate this problem, we can just substitute. And then after substituting, so we can just substitute. And after substituting, now we are left with something we can just punch into our calculator. So if you go on your calculator and you say sine of -20, then you will get an answer. So that's evaluation. We are testing each of these and finding the value of them. Yeah, evaluate, yeah. Yeah, so like basically investigate and then provide a value for this answer, for this given that the x and the y equal that. Is that sharp?
Yeah.
All right, so that's the second type of problem. This is supposed to be C, not B. Because when I look for B there, I'm seeing something else. So let's do number B, and it's the tan of x minus the tan of y. Just another thing, né? The English is also very important in the maths. The English is very important in the maths because the first batch of problems we did, they explicitly say determine the angle, right? And the angle is this, that is after the trig ratio. That's the angle. So we've determined those, we've determined those, right? The second batch of questions, these ones, where we are given the value for x and we're given the value for y, and I guess the authors or the whoever's testing us wants to see if we can provide a value to this expression given that the angles measure this much. So if we have the values for what x and y could be or are, we can then find out what sine of x minus y is or could be. We can find out what tan x minus tan y is or could be. Because we know what x is and we know what y is. So we can just punch in tan of x is, tan of y is, and then we subtract. So far, so good?
Yes, okay.
Yes, Wagala, so we're gonna substitute, and when we substitute x, we put in the place of x, we put 16. And here, in the place of y, we're gonna put 36. Then we're gonna go to our calculators. And we are going to look for the tan of 16. So it's 0,286 and minus 3610, which is 0,726 and and this answer is negative 0,4, I guess 440, because the 9 is like, if you round off from, like, if you truncate, if you cut the decimal, the irrational number from the first 9, then the number after it would round it up. So it would make the 9 a 10, and that 9 would make the 3 a 4, rounding it up like that. So that's why I write 0.44. That's how you round up. You look at the number after you've truncated. Is it less than or greater than 5? If it's greater than 5, it changes the number before you truncate. and then it takes it up. But if it's less than 5, you can just leave it as truncated at the thing. All right, so, and then we're gonna do G, ne? G is 2 cos of x plus cos of 3y. Now we're gonna substitute 2 times the cos of 16. So whatever the value of cos 16 is, we multiply it by 2. And we're going to add it to the value of cos of 3 times 36 degrees. Do you see that? Yeah, bo. So now we have
So
yeah,
where
ask.
the value sits before after is important.
So let's say you have a decimal, right? That one was negative 0,4397 don't
No, not in the truncating.
or not in the truncating.
No, I'm looking at 2 cos 16 plus cos 3y.
Oh yeah, what about it?
And the 3 are at different positions.
Yes, definitely, spot on. That is spot on.
So therefore,
How we solve it is how we work out the 2 cos 16, and how we work out the cos 3 times 36 is going to be different, and we're going to do that on our calculators. So the 3 times 36, you have to multiply the 36 times 3 and then take the cos of that. So it should give you 0,99 something. And the other one, you just take the cos of 16 and you multiply it by 2. So this one becomes 9.22 plus, I think this was 0,99 something. All right, and then we minus, let me open bracket.
maybe I'm doing this one wrong. 3 times 36. I'm getting 0,30.
Yeah, I need to look at that again because it seems I'm not doing the calculator use right. Yeah, so it's 3 by 36 and the cos of that. Yeah, so it's negative 0,309. You're right. Yes. And then this plus yeah, so then it becomes 1,922 minus 309, and that gives us 1,613 roughly. Do you get the same answer?
2 cos 16.
A
2 cos 16 degrees.
is how much?
No, it's 1,922.
Yeah. And then we have to subtract 309 coming. Hi. Okay. Yeah, Magdalene just joined us. Welcome. Yeah, so we're revising trig today, man. Let me just open that whiteboard for you. Google Jamboard. That's mine. So, okay, Nobutle, you said you got 1,922 for 2 cos 16, yeah? And then you got negative 0,309 for cos of 3 times 36, yeah?
Yeah.
All right, and then you then subtract the 0.309 from the 1.922, and I think the answer is 1.6 something.
Yeah.
All right, cool. But so far, how you find in the calculator use, is it nah?
Yeah, that's fine.
It's proper, okay. And you can link it to the concepts that we're doing, okay, ne?
Yeah.
All right. And then the last one is cosec of x minus y. Remember, cosec of an angle is 1 over the sine of the angle, and the sec of an angle is 1 over the cos of an angle, and the cotangent of an angle is 1 over the tan of that angle. So we're gonna refer to this because we don't have these specific trig ratios on our calculator. So now because we don't have them, we have to improvise. So in improvising, we can say this equals 1 over sine of x minus y. And then we substitute, so we have 1 over the sine of 16 minus 36. And this is 1 over the sine of negative 20 degrees. And if we go back to number A, that negative 0.342, let's just say 0.0, no, not 0.0, my bad. Let's just say 0.342 negative, and then we work out its inverse, then this becomes negative 2.924, and that's the answer.
Yeah.
But you see how we improvise for these trig ratios on our calculator?
Yeah.
Yeah, so you can simply hit the 1 over x button for any answer you get for sine. So if let's say you get sine is, this part here is, I'll just, it was 0 what? 42, 342. All right. So yeah, that's how you improvise on your calculator for that. So I wanted us to see that so you can identify that and be able to use it in any case. Because even in matric, even though the questions don't usually have cosec at times, some examiner would be spiteful and just add it just to see if, all the other years there was attention. So it's always best to be prepared. So knowing how to do those things at any given moment helps. Yeah. And then the last group of problems I want us to look at for solving trig equations are the following, right? So we're going to do all 6 of these for number 3. Starting with A, sine x equals 0.814. B, sine x is tan 45 degrees. C, and by the way, tan 45 degrees, you can also work out using special triangles. We did special triangles, yes?
Yes.
Yes, so the tan of 45 degrees would be opposite over adjacent, which would be 1 over 1. So already if you know your special triangles quite well, then you will know that this here equals 1. Tan 45 degrees, it equals 1. But in any case, we are yet to solve that problem. But I just thought it'd be nice to remember that we can still use this just to find out what this is. And if knowing this makes this, solving this particular equation simpler or quicker. All right. The third problem would be tan of 2x equals 3.123. The fourth one would be, oh, there's so much of tan here. Tan x equals 3 sine of 41 degrees. This one, we don't really have a special angle for it, but we know that it's going to be an irrational number because we've got an angle that's measurable. E, sine of 2x plus 45 equals 0, 123, and f would be the sine of x minus 10 degrees equals cos 57 degrees. So this one, these last two, we need to note that the angles are compound. And in metric, we've got compound angles where you will have the sine of alpha plus beta and it equals some identity. And we also have the sine of alpha minus beta, which equals a different identity. We also have the cos of alpha plus beta, which is a separate identity. And we also have the cos of alpha minus beta, which is its other identity. So I'm not going to tie these to these two just yet, but I just want you to keep in mind that solving for problems that might have a compound angle like this will, in metric, oftentimes require that we use one or more of these identities. Right? So identities become your best friend, but I'm only introducing the idea now whilst we're still solving equations because I want us to get familiar with solving equations in trig, right? And now these are double angles. This tan of 2x, that's a double angle. We've done a couple of problems that have double angles. And of course, there are also identities for sine of 2 theta and cos of 2 theta. These are compound angles. Compound for obvious reasons, you're adding stuff onto each other. And these are double angles for obvious reasons as well, because whatever angle you have, you multiply it by 2. Right? So just be aware that we're going to go into these concepts and we're going to move from solving these kinds of equations to doing work that's in grade 11. And I think that's where Magdalene would revise rather. And also Mashaku when she joins us. But hopefully you and I will be advanced in at least being on par with what we need to know for grade 11. Because immediately as we go past that stage, we're jumping into the metric work, right? And that's where we're gonna use a whole lot of not really complex, but engaging problems. And I say engaging deliberately because they are engaging. So yeah, starting off with the first, sine of x equals 0.814. Remember, we can just do the arc sine here, right? Ne? So arc sine of 814. Are you not on Jamboard? Or are you refreshing it?
Slide 8.
Slide 8, yeah. Slide 8, definitely. Yes. And then we can calculate 0.814. The arc sine of that gives us 54.489 degrees. But they say 2 decimal places. So since we got, I'm going to revise again the truncation versus rounding up or down. So we are supposed to round off to 2 decimal places. So we need to round off and look at this part. But how we do it, when we observe this part, this number is greater than 5. So it tells us that the next number must go up by 1. So what then happens is we round off to 2 decimal places. And this is, by the way, in any, I think in STEM, that's the rule. Because when we were doing chemistry, this is how they were teaching us to round off. And they called it significant figures. So 3 significant figures, 2 significant figures. But significant because depending on the accuracy, then the significance matters. So if I'm doing measurements in the surveying, engineering surveying, I have to measure to millimeter accuracy. Even the instruments allow that over distances of kilometers. But if I'm calculating the density of the either the concrete I need to pour on a curb on the side of a road, or the density of the soil that I need to compact, or the density I need to have after compacting the soil that's forming the foundation of a road or the abutment of a bridge, that I can't have decimals because it's immaterial. I don't need to measure the density of dirt 2.1 decimal. It's immaterial, it's pointless. So there's no significant figures there. But if I'm doing a surveying measurement over a distance of 5 kilometers and I'm using a precise instrument that measures to millimeters, then I have to include that, because any millimeter out of alignment, your road is going to have a step in it. And imagine you're driving 120 between Polokwane and Nelspruit, and the road suddenly has a step like a curb. It's going to be very uncomfortable, if not deadly. So that's the importance of rounding up and down to significant figures in engineering. And I would like to think that in other STEM fields it's the same. So how we round up in that process, or how we round in that process, they say two decimal places. So if it's 2 decimal places, we know after the 8 we're gonna stop. So after the yellow line we're gonna stop, but we have to look at what came after. So since it's larger than 5, we can up this by 1. So the answer then becomes 54.49 degrees. So that's how we round off.
Okay.
Yeah, so it comes 54.49 degrees. So we're going to use the same principle to round or to correct to 2 decimal places. The next one is sine of x equals tan of 45 degrees. Remember I mentioned a special triangle, one with 45-degree angle. So 45-degree angle and 90. That would be 1, 1, and the hypotenuse is square root of 2, right? So if this is adjacent and that's opposite, if you take Pythagoras, that's 1 squared plus 1 squared equals 2, and r equals square root of 2. So we don't take positive and negative because we know that it's a measurement of a distance, so it's by default positive, right? Anyway, back to this, the tan of 45 will equal y over x, which is 1 over 1, which is 1. So we know that then sine of x is 1. And what happens when we take the arc sine of 1?
Yeah.
What's the arc sine of 1?
Namhlanje uyagijima yonke.
I'm gijiming. You must. Okay. I did mention, hey, we're getting many now, so I have to make sure that as I accommodate you, I also accommodate our newbies as well. Because I want to make sure that I keep at a pace that covers all the stops. We need to keep pace that covers all the stops. Okay, but so far, where was I going too fast so that we can quickly recap?
No. I was writing, so.
Oh, you were writing.
It's 90 degrees.
It's 90 degrees, yeah?
90 degrees.
All right. So you see the pattern now. You see the pattern.
Yeah.
In some cases, we have to evaluate, so we'll be given the value of an angle, and then we must work out what the trig ratio is if the conditions are as. And then we also meet other problems where we have to determine the value of an angle if we're not given it, but we're given what the trig ratio of the angle equals. And there's a whole lot of things we can do. The last one, we just did a special triangle application. The other one is just your standard arc sine. But in all of them, the means to solve equations are consistent, is the point. The means to solve equations are consistent, is the point. Right. So number C, we've got tan of 2x equals 3.123. What can we do next? because we're determining the angle. So what we can do next is work out the arctan of 3,123, and then we can divide that answer by 2. My mistake, by 2, because we are applying multiplicative inverses. Ne? So after applying multiplicative inverses, then we will have a value for that. And what's the value? Anyone? Magdalene? What's the value for arctan of 3.123 divided by 2? So 3.123.
36.122 something.
Yeah, it is that. So it's 36, ne? 36.12 degrees. Must put the degrees because it's an angle measure. If you don't have the units, it's incorrect, because what are you describing? You'll get asked that question, Alan.
Yeah.
Yeah, so you want to eliminate those kinds of questions, because what they do, and I'm sure you understand in a professional capacity, they mean, no, what lame, my boss, what are you talking about? Yeah, if we don't have units, we don't know what we're talking about. But if we have units, then we know we're speaking about a specific thing. Then we have tan of x equals 3 sine of 41 degrees. Have I been putting angles in the other ones? Yes, I have. All right. Then here, we can first calculate what sine 41 is, multiply it by 3, and then do the arctan of it. But I prefer to use my math to solve for the equation without solving for the without evaluating the answer. Because I know if I applied the correct math in solving for the unknown, then when I evaluate the answer, I'll get a correct answer anyway. So I'm just going to go ahead and do my step. But anyone is welcome to work out first sine 41 multiplied by 3, and then work out the arctan of that answer. You're more than welcome to do that. Try that, do that, and then let's see if we get to the same answer. So my answer is going to be arctan of 3 sine of 41 degrees, and this will equal so 41 sine, and then multiply by 3, and then it's how much?
63.065.
Yeah, so 0.07 degrees. Yeah. You also get the same, Magdalene. Okay. All right. Then we do E, not for ETV, but just E.
Oh, come on.
So I'm just going to put a degree there on the 45, because, I mean, it's an angle. It's supposed to be an angle. Ne? So the sine of 2x plus 45 equals 0,123. Right? And remember, compound angle. I'm planting seeds, compound angles. We're going to go there. So yeah, here we can just simply jump straight into the arc sine of 0,123, and that equals 2x plus 45 degrees. So what's arc sine of 123? What's the answer there?
It's 7,06.
Yes, 100%. And now we need to do additive inverses on both sides, so that we have 2x equals arc sine of that, which is 7,065 minus 45 degrees. Do you get it? subtracted 45 on either side of the equation, and then x is gonna be that whole thing divide by 2, and that equals something. So we're gonna subtract 45 here. So minus 45 is negative 37,9347 ton, and then we must divide that by 2, and that gives us negative 18,97 degrees. Anyone got a different answer?
Nope, same answer. Thank you.
Magdalene, you also got same answer? Alright, cool. Then we're gonna do F, which is the last one for trig equations, because after trig equations, we are going to define ratios in different Cartesian plane quadrants. We're gonna do that. So let's quickly solve this one. It's the sine of x minus 10. It's a compound angle, and this equals the cos of 57 degrees. Yeah. So Magdalene, you're having an advantage, even though it's work from last year. Your advantage is you are revising stuff that you should be much quicker at. So be very happy of the fact that you're revising and you get time to revise with someone who's sitting next to you and revising with you. So be very proud of that, Jorge. You are getting a very deep kind of revision. Anyway, here we can do arcsine as well. Cos 57 is going to give us an irrational number. What's the value for that?
It's 0.544.
100%. And then we must take the arcsine of that. Yeah? We must take the arcsine of that and add 10 to it, because we do additive inverses in the other step. So this, the arcsine of it is how much?
For the trigonometric 8.
Wait, if we take the arcsine of cos 57,
Plus 10.
I said 33. Wait, I need to do this again, just so. So it's 57 degrees.
33.
It's 33, yeah? Yeah, so it's 57 cos. And then we take the arcsine of that, gives us 33. Then we add 10. So Magdalene, do you see why we always need to revise stuff from back, even though we think we're ahead? Just because we're in grade 11, 12 doesn't mean if the basics for grade 10 are lacking, we should overlook them. We need to regress sometimes, and that can help us progress. Ne? Yeah, sometimes you must regress so you can progress. It's no shame. It's something that happens in a lot of places and in life as well. Anyway, defining ratios in the Cartesian plane. Right, so equations, Nobushi, how are you with them? How are you finding them so far? We've done the bulk of the work we need to do for equations. How are you finding them so far?
Yeah. I can rest.
You can rest. But like, I guess I'm interested in finding out, like, are they clear? Do you see the connection between the stuff we do in equations in algebra and how we can put it in trig? If that's a checkpoint for you, then I'm happy we can proceed.
I think the only place where we'd spend some more time is your cosecs.
Oh yeah, we haven't done a lot of those. Yes.
Yeah.
We haven't done a lot of those. But look, you can always give me a shout and say, listen, I was doing some practice by myself, but I came across this one. Do you think we can play with it? And then I can explain. Or you can try it. I'd encourage you try it. And if you get stuck, you just give me a call and then we can sit down and look at it. Ne?
Yeah.
Yeah, we can do that. But you know the long and short of it, because they are reciprocals, you first take the original trig ratio, work out the trig ratio for that angle, and then you do the 1 over x. That will give you the reciprocal. That's the long and short of it. Anyway, if we recall correctly, from all our definitions in trig ratios, all our trig ratios have been defined using, and that doesn't look so right angle triangle. We were defining them using right angled triangles, yes? And the importance of this is that it makes it simple because it doesn't matter how the triangle is oriented. It can be like this. Maybe not. It can be like, I want to put the right angle here. I want to put the right angle like so. Yes, it can be like that. It can be like that. Yeah, one. And as long as we have a specific angle that we're concerned about, we'll always use R for hypotenuse and whatever x and y are, depending on the angle that we're looking at. Right? Now, or rather opposite adjacent. Let me rather put opposite adjacent hypotenuse, yeah. Because I want to show how they link to this. So our definitions were that sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. So this would be adjacent, opposite, hypotenuse, adjacent, hypotenuse, opposite, hypotenuse, adjacent, opposite, right? So we know that this maps to our hypotenuse, this to our adjacent, and this to our opposite. So now we're going to take all of this and translate it to our xy plane, right? And this helps us because we get distances or lengths of some of the sides. For an example, if we have on the x-axis from 0 to 1, 2, 3, and on the y-axis we also have 1, 2, and 3. Moscow fish. Excuse. Sorry, flu. Yo, that means I have to run twice now. So that my lungs don't get things in there. It's fine. But anyway, so we've defined using trig ratios, but we can extend them to angles okay. So it's important to note, we can extend definitions to any angle, right? So it doesn't matter if our angle is obtuse or acute or a 90-degree angle. And that is because if we note the definitions of trig, they don't necessarily rely on the lengths of the sides of the triangle. Because how do you know the lengths of the side of a triangle when you know that the angle is 26 degrees? You see? So because you don't know the lengths of the height or the opposite or the adjacent, then we can just work out the cos or sine or tan directly. And we'll still get the value whether we know the side's length or not. But that's because the trig ratios depend on the size of the angle only. But now when we plot on a Cartesian plane and then we draw a line from the origin and to a certain point, let's say the point is P, 2 is to 3, right? So point P, x is 2, y is 3. Ne? So what happens when we do that is we introduce sides whose lengths we know, and because we don't know the angle of inclination, so let me use blue for hypotenuse. So because we don't know this angle of inclination, we can estimate it And we can estimate it using the values that we know for x, which corresponds to the horizontal distance, the x distance. And we also can use the y value, which corresponds to the vertical or the height at this point that we're interested in, right? And what happens is the 3 is represented by, which literally is this distance here. Because they're parallel, they must be equal, right? We did a couple of shapes, some parallel lines, and this would be 2 units. My English is lumbering me there. Mlume. Mlume English. So, yeah, so we're gonna do specific points. So let's start with point P, right, in our learning guide. Start with point P, and then we're gonna go to point Q, all right? So, just analyzing point P. Right. So when we define trig ratios according to the angle A, theta. Okay, I'll call it theta. Or rather, let's call it A, so that it's easier to explain using the same learning guide. So it's not so different, right? So this angle goes from the horizontal x-axis to the line that is blue, which forms our hypotenuse, right? And we can see that because the coordinates are 2, 3, the 2 corresponds to x value, and the 3 corresponds to a y value. This means that we can use these trig ratios exactly the same, because the opposite is the y value and the adjacent is the x value. So we're going to use the same definitions for trig ratios and apply them on here, such that if we work out the tan of the angle A, it'll be, our opposite is 3 and our adjacent is 2. Right. So when we do the arctan calculation, we get an angle that equals roughly 56.3 degrees. Ne? If we do the same calculation for a point that's a mirror reflection of point P, so about the y-axis, so I'm using the English very deliberately, a mirror reflection of point P about the y-axis. So in other words, Nobuhle, you ever use Microsoft Paint?
Yeah,
Long time ago. Do you recall seeing a button that looks like 2 triangles, and they have a split line, and the other triangle looks like this?
A mirror image.
Mirror image, yeah. Yes. So that button is a mirror image. So it means, so when you reflect your face on the mirror, that face is reflected about the surface of the mirror. That's the point where the reflection happens. The same way of thinking, just as with the button that mirrors something in Paint or drawing software, we apply it in maths, and that's where those come from, by the way. Those features in the software come from, because it takes a bit of math to build a computer, and obviously if you're going to program it, you have to use a bit of language, and maths is part of it as well. So anyway, point Q is mirrored about the y-axis. So that means only the x value changes to a negative value, but the y value remains consistent. So that means to go up from the x-axis where x is -2 to where y is 3, you go up 3 units, like in point P. And to go to 0 to the point -2, you go -2 units. And that gives us a different triangle who's in the second quadrant, by the way. So this triangle who's in the second quadrant, we're gonna do similar analysis to that line. All right, so I'm gonna get to how we find cos and sine, but I just want us to work with this one because it also touches on an important thing that we do in, I guess, from grade 11 onwards, which is where you have 180 degrees minus theta, for example, which are compound angles, but they're also, what do you call them? In grade 12, they have the name set out nice here in the grade 12 guide. Not special angles. Reduction formulae, yes, because you have to reduce the angle from being compound to being simple, like we've been taught. That's where trig starts, like at the beginning of trig. Those are simple angles. So I want you to note that this is going to give us a compound angle where we're going to have to use some kind of reduction. But anyway, that's angle A. Now angle B is said to go from the positive x-axis to the second blue line. So that's angle B over there. And we have to work it out. So for point Q, we can still work out the angle between the negative x-axis and the hypotenuse in the second quadrant. And we're going to use the same trig ratio of tan, but for the angle alpha. And we're going to use that alpha to find the value of y. Of B, of angle B. Now when we substitute, the opposite is 3 and the adjacent is -2, or rather it's 2. Because if we're just looking at the triangle, it doesn't matter which direction the thing is, the lines are going, the measurement is exact. It's not negative, it's not positive, it's just a number. So that's why there's no negative there, because we're just focusing on the triangle and we're looking at the point PQ. We're using the point PQ to thingy. So but I just want to see something. If we just calculate, let's say 3 divided by 2, and then we take the arctan. Yeah. Also, we can't take the negative because it's going to give us a negative angle. And a negative angle is found in the fourth quadrant. And in the fourth quadrant, then we're counting clockwise for our angles. That's where negative angles are. So that's why we can't have a -2 there. That's the second reason. Yeah. So we're just going to work this out, and then we'll get alpha is 56.3 degrees. So now, how we find the angle beta? Since we know the measurement of this angle here, alpha, if the sum of angles on a straight line is 180 degrees, then this angle plus this angle on the right of the second blue line, the second blue hypotenuse, they must give us 180 degrees. So in other words, beta, or rather B, plus the angle alpha must equal 180 degrees, and angle B will equal 180 degrees minus alpha, which is 180 degrees minus 56.3 degrees, and the answer there is 123.7 degrees. Not Celsius because it's not temperature, it's angles. Ne? And we can still use Pythagoras theorem. Remember Pythagoras theorem, you just take r squared, which is that, and you sum it to x squared, or rather you sum x squared plus y squared and you equate the two. And this way you'll find what r is. But if we quickly do it, r squared will be 2 squared plus 3 squared, which is 4 plus 9. Yeah, 4 plus 9, which is 13, is r squared. Therefore, r is square root of 13. Again, we don't do positive or negative for if we're using Pythagoras. We don't do plus minus square root of, because it's a distance, it's exact. You can't measure negative 30 millimeters on your ruler. Yeah, that's the whole point. Yeah, that's what I want to say. Yeah. Then the next thing is we can find any angle. Oh, by the way, the same way we did this tan here, we can also do the reciprocals. So 1 over sine would be cosec. We can do them the same way. So if you do come across a problem where it requires that you do that, definitely you can do that for reciprocals. Then we can also find any angle. So if we have a Cartesian axis, Magdalene, do you know why it's called Cartesian plane? Do you know why it's called Cartesian plane? You don't know why. And I think this is the problem with teaching and learning maths and science in South Africa. The history, no one really cares about it because people choose maths and science because they avoid history. No, honestly, I chose maths and science because I was avoiding history. But as I did the math problem, I realized that there was so much history. Like Thomas calculus, yeah, first year and second year maths in varsity. Every page had a bit of history about where a concept comes from. If not a history, an example. From how integral and differential calculus were discovered at the same time by two people in different parts of the world, to how you can use the behavior of a graph of tan to model the behavior of some insects. Like they just disappear and then suddenly and then there's flies all over the house. So you can model that using math, and I think the trig ratio tan maps that lifespan of flies or insects like that have a larval life stage. Because at some point they just disappear and you don't know where they are. And jiggy konimpugan. So the point is, we're not taught the history of some of these things, so we kind of don't see their relevance. But it's called Cartesian plane because the person who came up with it was René Descartes, a French man, right? René Descartes was French. He's known as a philosopher and mathematician and I think other things. But one of the things that's important in his life that happened is that he lost his mind at some point.
Okay.
Yeah, he went insane. And then when he bounced back, he came up with very interesting philosophical concepts like I think, therefore I am. Have you heard those words before? You know those words, Magdalene? I think, therefore I am.
No.
Yes.
It's because I think that I exist. My consciousness creates my reality.
Okay.
I struggle with maths because I think I struggle with maths.
Oh, okay. No, I
My consciousness creates my reality. So after coming up with those things and in the process of, I'm not sure exactly where the timeline sits, but one of the things he did become famous for after bouncing back from his bout with mental illness was developing a way to map coordinates. So if something is moving laterally, how does it relate to something that's moving across me, horizontally? So then he made experimentation, documented data, whatever, did the whole scientific process like you're taught in science. And then the Cartesian axis came because it comes after his name, Descartes. There's a Cartes at the end there.
Okay.
So because maths were done in Latin around his time, when they made their way to being part of the classroom setup, and English was now seeing an opportunity. The English was seeing an opportunity to export their language. Then they converted all the Latin works from Isaac Newton, etc., and all of them into English. And because they had to Englishize the name Descartes, and in honor of him anyway, it's a Cartesian plane. Cartesian plane. That's where it comes from. So, how much about life did you learn, Magdalene, just from that? You see, so part of teaching maths and science also has to do with teaching the history, because if we don't teach the history of some of these things, we lose meaning of why they are relevant, because these things are not just part of the classroom setups for fun. They were solving real problems in the world that were emerging at the time. Problems that we don't even think are problems today, because the maths and science have solved them so much we don't even think that they're problems. And just to add, there's a scientist called Carl Sagan, and I always say this quote, it's my favorite. He says something along the lines of, we live in a world that is exquisitely reliant on maths and science, but hardly anyone knows anything about the maths and science and technology. So it explains why in America people have an iPhone without knowing that kids in DRC are mining that part that goes into a chip with their bare hands, and we wonder why the world is unbalanced. But anyway, I'm gonna stop philosophizing. So Cartesian axis comes from René Descartes, and we now use it to draw a circle with a center at the origin. I'm gonna try and draw a circle, so please bear with me if it's not round. So there's our circle. Not circle center, but a circle with a center at O. There's X, there's Y. And somewhere on the circumference of our circle, we have a point. We'll call it P again, for convenience. Not because my classes are Mr. P's classes, but... All right, so yeah, that blue line is our radius, naturally, because if this is a circle with an origin O, then any line that connects the origin or the center of the circle to the radius, to the circumference, is the radius. That's just how circles are. And then we look at the angle formed between the positive x-axis and that radius, or the ray, radius, ray, etc. And we'll call it theta for now. All right. If we close up the triangle that is formed within this this quadrant, if we close up a shape here and make a triangle, because trigonometry is the measurement of triangles. If we close that up, then we will have a length y that corresponds to the value here at y, and a height rather, and we'll also have a distance x, which will correspond to that value there, and I guess there as well. So if you pay attention, you'll see also a lot of the stuff that's from geometry. It shows up, it goes away. I mean, this is a square, and a square is a parallelogram, and when we have parallelograms, the sides are equal and parallel. So it's just one of those things you can notice as you're doing the math, right? So we're going to number our quadrants. The one in which our x and y are defined is quadrant 1. The one to the left of it is quadrant 2. The one below the quadrant 2 is quadrant 3. And the one to the right of quadrant 3 is quadrant 4. And we use what is called a cast diagram, right? And the importance of this cast is the following. Right. When we use the Cartesian axis to find any angle, then our angle may not necessarily be positive all the time. Our angles may not necessarily be positive all the time. And if we know the values of x, y, and r, then we can locate where on this Cartesian axis system that angle is situated. It can be in this quadrant or that quadrant or this quadrant. It doesn't matter. But we are and that's because we are learning how to identify, how to spot where that angle sits. That one. And the second thing we must also note, all the trig ratios, your basic ones, sine, cos, and tan, and your reciprocals, cosec, sec, and cot, we can all express them using x, y, and r, right? But now the importance of cast is the following. Where we see C, we will associate any trig ratio or reciprocal that associates with cosine. So cosine plus reciprocal. Oh, I wrote repick. Yo, mlume. Mlume. All right. And that's quadrant 4. Quadrant 1 is where all the trig ratios are positive. Quadrant 2 is only where sine plus its reciprocal are positive. And quadrant 3 is where tangent and reciprocal are positive. And this knowledge, this cast is very important from this day. Like, please, don't ever forget it. Like, always remember it, because when you are doing your reduction formulae and you have to reduce angles from, let's say you're reducing an angle from 480 degrees, you're gonna have to use something like 360 plus something to reduce it. And that will tell you which quadrant where the angle sits. And the cast reference will always remind you, because restatile that trig ratio when cos or sine or tan was in this quadrant, if we reduce it and its sign changes, then this is the result. So this cast is very important because in our metric maths, it becomes a deciding factor for whether or not the end result of a reduced formula is positive or negative. And that correct application is what gets you all the marks or none of the marks. All the marks or none of the marks, right? So all this in these I've just explained, but yeah. And then the other thing that we must also pay attention to with this cast diagram is the following, right? Here, x, y are both positive. Here, x is positive, y is negative. Here, y and x are both negative. And here, x is negative, but y is positive. So because our trig ratio for sine relies on y, and our trig ratio for cosec relies on y, wherever y is positive, those ratios will be positive. Because wherever x is positive, so any quadrant where the x value is positive, any trig ratio that has to do with cosine, be it cosine or its reciprocal secant, will be positive. And in the third quadrant, where both sine, or rather x and y are negative, then negative divided by negative will give us positive. So then that means tan is positive in there, or rather, yeah. But it means sine and cos are negative there. Yeah, but it means sine and cos are negative there, but only tan is positive because you're going to have a negative y divided by a negative x, and that's going to give you a positive result. So tan is by default positive in there, as is reciprocal is. But any other trig ratio or reciprocal is negative in the third quadrant. So that's the long and short of cast. And then lastly, on the same cast diagram, and Nobuhle, remember I kept mentioning Hore, we can think of these trig functions as both circles, triangles, and waves. I think I did mention something like that. And we're getting slowly into that, right? So we're going to take our same Cartesian axis. It's a bit too close to the left. And that has nothing to do with politics, by the way. That was the left of the screen. So there's our circle. That's y, that's x. And this is a very important thing that we learn in trig ratios as functions, right? So I'm bridging the two because Nobuhle, you and I did do functions, but we didn't do trig functions. So I want to again come back to this sketch that I like so much, right? If we think of this circle as a unit circle, right, the radius equals 1 from 0 as a unit circle. And we have, doesn't matter what the angle measure is really, but we'll just call that theta. And all the way to the circumference, we have our radius there. Right, so if this is y, then this will map to theta. So the function, so this is the, I guess we can call this Cartesian plane illustration. Versus y equals, or rather function of theta, right? So the Cartesian plane illustrates how these work in terms of x and y. But that doesn't mean it ends there with trig. And we're going to illustrate why. We're going to demonstrate why. It doesn't just end there with trig. Remember I kept saying that sine and cos always greater than or equal to -1 or less than or equal to +1. So the wave function or the wave form of our trig ratios for sine and cos oscillate between 1 and -1. Always, right? Our wave function oscillates between -1 and 1, always. And that's because if you look at this as a circle, okay. Sorry, you have a guest there?
I was not going to stay.
Oh, okay.
Yes, and then I normally should have breakfast.
Oh, okay.
Yeah. And then oh yeah, man, what's up?
Leraka invoice.
No, everything.
Everything. Kita romela invoice today. I finish in class and then I from there.
Yeah.
Yeah, and then for now that's all I play that class.
Okay, sure.
All right.
After.
Bye
Bye-bye.
bye.
Ah, that's my shit. I got. Coca-Cola.
Machine. Oh. All right. So where were we? Yes, I was saying. So if we look at this thing, the wave function that we're gonna draw there illustrates how this point on the circle, moves between 1 and -1. Nobuhle, do you follow? Hello? Wait. I'm not seeing.
Hello, yes, I am following, I'm listening.
Oh, okay. Because I'm not seeing you write on a Jamboard to say, hey, crisis call.
Oh, no.
Yeah. But like, do you understand what I'm saying, Jorge? We're going to look at this radius, this point here on the circumference, and
Yes.
how it moves around the circumference. And we're going to look at that point as if we're looking into the page of the king. On the xy plane, we're looking at this function as if we made an illustration with a spring. Yes, if you have a spring like that, when you look at it from this side, it just looks like this. Remember, when we look at a spring from the side, it looks like a tube. But when we tilt it to the side and we look at it from sideways, then it becomes a spring like this. So in a similar way, we're doing that. And this is when we're looking at the spring as though from the one end, so it looks like a tube. And then we're going to expand that spring such that it looks something like this. And we're going to look at angles between, remember theta goes from 0 to 360 degrees. So y as a function of theta changes when we put it in function form, where theta now goes from 0 to 360 degrees, but it can also go in the negative direction, just by the way. But if theta goes like that, then we know that theta starts from 0. Some point it passes 90 degrees. At another, 180 degrees. Okay, maybe that's a little too close. That's 180 degrees. At another, 270 degrees. And at another point, 360 degrees, right? And we can look at it also in the opposite direction because we have negative angles. So far, is it yeah, Zwaga? Yeah, Vaga?
Yeah.
So. Right. So when we move from xy function to wave function, our dynamics change because our independent variable is theta, and we need to line it up like this, put it in a line to the left and to the right, because it goes over and above. It starts from 0 to 360, and it can go above, and it can also go below 0 degrees into the negative infinite direction. And that just means that this point here can go around this circle so many times. But when this theta increases, so here it's between 0 degrees and 90 degrees. And as it increases, it goes from 90 degrees to 180 degrees. So that means we're going in this direction on our function. But on our xy plane, we're just going in a circle. We just shifted quadrant. So that's why I said two ways of thinking about it, as a circle and as a wave. As a circle and as a wave. So as a circle, our angle increases. So it starts from 0 to 90, then 90 to 180, then 180 to 270, and then 270 to 360. So I'll just put those angles there for reference, because that's the trajectory that theta follows on the xy, and then yeah. So what?
Nothing.
Yeah, so yeah, then the other thing is, one thing that's important to note, and this is the case for tan only, ne? And that's why I'm drawing red lines on the 270 degrees and the 90 degree angles. I'm drawing red lines to show that they are asymptotes. Remember I said that in some cases, some insects have a larval stage, but then you don't know what happens before the larval stage. It's like they just don't exist when you study them. And then suddenly the larvae become insects that are infesting, and then they increase in population to a point where they reach a maximum, and then they suddenly just die out. And then after a couple of days, the same cycle goes on. So that looks something like, if I'm to illustrate with a what's this? laser pointer, it looks like you start there, from out of nowhere something emerges, and then you reach a point where you start replicating infinitely, and then you just stop existing, and then the cycle repeats again. So that's how the tan graph works. But we're gonna start with sine because it's the convention. So I'll put the sine graph in blue, right? So sine theta will be blue. I'll put cos in green, and I'll put tan in yellow. Ne? This way we'll be able to identify what's going on despite the mess, right? And why I'm going through all this trouble is because the next part in this book explains special angles in the Cartesian plane. And those special angles are really 0, 30 degrees, 45, 60, and 90. And I guess we can show them here as well on the graphs and on the Cartesian plane. But I want us to overarch the whole trig thing from both a problem thing and a function thing in the next 10 minutes so we can wrap up. Right, so starting with sine, when we are at 0 degrees, sine depends on y, remember? Because sine theta is y over r. So if y is 0, what's the value of sine at 0 degrees? Because it's 0 over r. Yeah, wait, at 0 degrees. At 0 degrees, sine is 0. And then at 90 degrees, ne, the value for y is the same as the value for r. So the ratio for sine is y over r, which is 1 over 1, and it gives us a maximum value of 1. At 180 degrees, y goes back to 0. So we'll mark it there. At 270 degrees, y is negative 1. So it gives us here. And at 360 again, that's 0. So what eventually happens is our graph looks something like this. So it's smooth because the trajectory around the circle as this point P makes it around and around is smooth. So it oscillates. It oscillates. You know what an oscillation means? Okay, so you did waveforms in physics, right?
Yeah.
Right. When you have that, what's the space between where a wave starts and where it ends?
A gap.
Not a gap. And we're gonna do that, by the way. You and I know within physics. We still have to do that, yes. What is it called? That's our board. Okay, it's fine. So whenever a graph starts at point 0, oscillates and trajects at, that's an oscillation.
Okay.
So when it repeats, it's oscillations.
Okay.
And then they have a frequency.
Yes.
This here is the wavelength. This here is the amplitude. From 0 to 1 is the amplitude, the maximum height from where it starts to where it reaches. Yeah. Yes. So yeah. Then the same graph in the negative, when we follow the path of the point at P, I'll just put there P. Ne? That same graph, when we follow its trajectory in the opposite direction, it goes from 0 degrees to negative 90 to negative 180 to negative 270 to negative 360 degrees. So now we're going to map the points. At 0 degrees, sine is 0. That checks. At negative 90 degrees, y is negative 1. Therefore, sine is negative. So we're going to get negative 1. Negative 1 divided by r is 1 because it's a unit circle. So then we get negative 1. Then at negative 180 degrees, y goes again to 0. At negative 270 degrees, y is positive, so we get a positive result. But again at 360, y is 0 again. So
We're
then,
still at sine, or we're doing cos.
no, we're still at sine.
Oh,
We're mapping it as an oscillation in both the positive and negative y direction, or theta direction, sorry. So I had to, yeah. These graphs, mlume graph, mlume. Yo, I tried shame. I wish there was a plugin on this thing at Jamboard for ChatGPT to sketch the graph for me. Do you know ChatGPT, Magdalene? Do you know what ChatGPT is?
No.
You know when you go on Google and you say, what is the capital city of South Africa? And then it returns results. Now imagine Google having a conversation with you and you can ask it. So if there are 3 capital cities in South Africa, which one is which and why? Then it will tell you. Or Pretoria is administrative, so that's like London or Washington or whatever.
Yeah.
Cape Town is legislative, that's where our laws are passed. Bloemfontein is judicial because that's where our very special court matters that are below the constitutional level are resolved, like special court of appeals is there, etc. So ChatGPT will have a conversation with you and tell you these things.
Oh, yeah.
So what it can do now, it can create art.
Yeah.
So you can create something that looks like this and print it on a t-shirt and sell it. That's what ChatGPT can do.
Okay.
So I'm saying I wish I had a plugin for ChatGPT so it can draw this graph for me so I don't have to. Yeah. Anyway, now we're gonna do cos. And remember I kept mentioning co-functions, ne?
yeah.
Yeah, so now we're gonna go back to it again. Co-functions. So sine and cosine are co-functions of each other. That also means their reciprocals will be co-functions of each other. So sec and cosec would be co-functions of each other. In other words, they differ by 90 degrees. Right? They differ by 90 degrees.
Okay.
And it makes sense because when we look at just any right-angled triangle and we call this theta, then that angle will be 90 degrees minus theta. And that's the basis of co-functioning. Right? The difference in 90 degrees, the shift in 90 degrees. And even when we do these in identity form, you'll see that when you start out with cos of 90 degrees minus and when you do the co-function shift, it changes to sine. Because it must change to its co-function. Anyway, back to our graph where theta is 0 degrees, x is 1. Where our theta is 0 degrees, the value of x is 1. Because our radius will be somewhere here. Great, it doesn't change shape. It doesn't just cut and then come there. It remains the same because that's that point circling from there and going around and around the circle. So because it starts there, the value of x from 0 to the circumference of the unit circle is 1, which is the same as the radius because it's a unit circle. Unit because 1 means uni. So at 0 degrees, cos is 1. Right? Then at 90 degrees, at this part here, what's the value of x? It's 0. So if the value of x is 0, then our graph comes here at 0 degrees. Sorry, at 0, y equals 0 for 90 degrees. At 180 degrees, which is this point here, x equals negative 1. That means the trig ratio is going to have a negative value. And at 270 degrees, x is again 0. So we have a 0 there. But at 360 degrees, x is again 1. So we will have x going up there. And our graph curve is going to curve something like this. Ne? And then when we do the same in reverse, In other words, for negative angles, starting with 0 degrees, going to negative 90, negative 180, negative 270, and negative 360. Then at 0 degrees, cos is still 1. At negative 90, cos goes to 0. At negative 180, cos goes to negative 1. At negative 270, cos goes to 0. And then again at negative 360, cos goes to 1. So then our wave rather curves something like this. Again, not straight. Always curving there. All right. So you see the 90-degree difference between the two graphs.
Yeah.
They're literally shifted from each other by 90 degrees. Can you see that on the graph, Nobush?
Yes, I can.
Yeah. And the last trig function we're going to do is tan, right? And now the red lines, the red dotted lines are there for specific reasons because they're going to mark our asymptotes. Ne?
Asymptote, you say.
Asymptote, yes. Asymptote. And asymptote is also a word we use when we define hyperbolic functions. Because the x and y axes, the graph doesn't touch them. The graph doesn't touch them, so they're asymptotic. What does asymptotic mean? Yeah, let's start there. Asymptotic meaning. Asymptotic, right. Means approaching a limit or value as some variable tends to infinity. Okay, so it means relating to an asymptote or lines, approaching them nearer and nearer, but never touching them or crossing them. That's what asymptotes mean. That's why in the insect example I used, where you can map them out using a tan graph. Actually, I should look for that example. In that one, like they suddenly disappear and they suddenly appear. So where does that happen? It happens near the asymptote. So asymptote in modeling the lifespan of some insects. Okay, I'm gonna look for such a thing, and then I'll have to put it on thing. I'd love to look for such a thing and then put it on Classroom, so that you can see what I'm talking about. Because I promise you, we did do something like that in engineering maths, and it was a problem about insects that behave like flies. And what was interesting was to note that at some point they suddenly disappear, and then at some point they suddenly appear. And the graph looks almost something like tan, but it was asymptotic. But I'll look for something like that. Okay, it's fine. Not necessary now. But anyway, let's go back here. So we're going to go for tan. Tan's ratio is defined by x and y.
Asymptotic analysis of an insect dispersal.
Yeah. Something like that, yes. Something like that. So anyway, tan uses x and y, right? Wait, so tan uses x and y. So at 0 degrees, x is 1, but y is 0. Can you see that? At 0 degrees, x is 1, but y is 0. And because tan is y over x, then it becomes 0 over 1, which is 0. Maybe we might need to look at angles like 30 degrees and 45 degrees. So let's do 45 degrees. But we know that at 45 degrees, tan is 1, right? So when theta goes to 45 degrees, tan goes to 1. But if we go to like tan 89, for example, or rather, let's do it like this. Magdalene, on your calculator, I want us to do some simple numeric drilling. Eh? So we're going to look for 1 and work out its tan. It's 0.01, right? Or maybe not. I get a tan 45 is 1. Let's do tan of 46. So it's 1.03. It's showing that it's increasing. Okay. Let's try 50 degrees. So it's 1.191. Oh, so it's definitely increasing. So there's an upward trajectory. After tan of 45, we go above 1. So then what happens when we get closer to 90 degrees? So let's work out the tan of 89 degrees. We get 57. Let's work out the tan of 89.9 degrees.
57, 572.
Yeah, 89.9 degrees. I want you guys to see something, yeah? Then we're gonna do tan of 89.99.
It'll take us almost to 600. Are you sure?
Yeah. Right now we're just playing with some number values, but it's because we wanna.
5,000.
Yes, that's 89.99. So I want you to do now tan of 89.999. So 3 nines after the decimal. And tell me what the value is.
5,057.
57,000. When you add another 9 to the decimal, what happens? It becomes
572.
502,000. So are you seeing how exponentially it's rising after 1? And as you get closer and closer and closer to the asymptote, it keeps exponentially rising. So what eventually happens is our graph does something like this. Right? Yeah, one. And because as soon as you hit 90, even in analytical geometry, we use tan to test for the gradients using tan, right? If a gradient is vertical, like let's say it runs from the x-axis and goes parallel to the y-axis, that gradient is not defined because we don't have a change in y or a change in x. Oh my word, did I just make a connection in my mind between gradient and tan? Wow. I just didn't know how to explain it properly, but yeah. Anyway, so our tan graph looks something like this. Even if you say tan of, let's do tan of 91 degrees. It's gonna give you a negative answer.
Negative 57.
Okay, then do tan of 91.1 degrees.
Negative 52.
Negative. Okay, and then if we do 0.11, oh no. I wanna do this. Sorry. 91.1 tan.
1.9.
I wanna do. Oh yeah, 91. Oh, let's do this. 0.00000001. Yes. And then we work out the tan of that. Oh no. It's supposed to be 0.99. So let's say 91.9. Yes. And then we work out the tan. It's negative 30, right? And if we do the tan of 91.99, what does that give us? 0.99.
28.78.
Oh, okay, good. It's reducing. Yeah?
Yeah.
91.999.
Let's take a break so I can have my nap.
Okay, 91 point. But anyway, long and short of it, we covered two important chapters rather. Visualizing our trig on the xy plane and doing the ratios there, but also visualizing it in function form. And the function form is important because it adds to the functions work that we did earlier.